Hello everybody, welcome to the Chapter 7 video. Today we are talking about intermolecular forces and solids. We have a very similar chapter next week as well with Chapter 8, which is intermolecular forces and liquids. So these two chapters together, I should say, are probably the most important for your AP exam. About 20% on average of your questions come from what they call Unit 3 intermolecular forces. So it include stuff from both of these PowerPoints, and Chapter 9 is about gases. So kind of all these states of matter, intermolecular forces, takes up about 20% of the test. Lots of FRQ questions are written about the kinds of intermolecular forces and how they relate to boiling and melting points and the properties of solids and solutions and stuff like that. So probably the most important chapters coming up for us for like getting a good grade on the test. Okay? The stuff is a lot of what we do in honors chem with intermolecular forces, just kind of ramped up, very similar to like the Lewis structure stuff, where you knew how to draw Lewis structures in honors chem, but we added like all this extra detail to it. And there's some similar stuff sort of with that today. So let's go ahead and get started. The word intermolecular force is what we're going to start with. The force that holds a single molecule together, like a single molecule holds it together, is called an intramolecular force. But the force that holds a group of molecules together, many of them attached and attracted to each other, is called an intermolecular force. So we talked about intramolecular forces. The two types that we have that we really focused on were covalent bonding and ionic bonding. An intramolecular force is just a bond that holds a molecule together. Intermolecular forces aren't bonds, but they're kind of similar. There are reasons that many molecules would be attracted to each other. They're things like London dispersion forces, dipole-dipole forces, and hydrogen bonding. And they're not as strong as those intramolecular forces, but they explain a lot about why certain things tend to stick together in reactions, or why certain things are attracted to other things, or why things are solid, liquid, or gas at room temperature. So it's a very incredibly important sort of section of chemistry we're going to talk about today. So, intermolecular forces, abbreviate IMF, are forces that hold molecules together. And almost every molecule experiences some types of intermolecular forces, at least some amount of them, and that's what holds things in groups together, right? Think about like as like a drop of liquid holding itself together and not just like spreading out. There are intermolecular forces in that water, kind of making the water tend to stick together. And that's true for all sorts of different types of matter that we know about. And just kind of an example, this isn't exactly like a one-to-one comparison, but think about like space and the universe as a whole, right? It's a giant empty void. There's nothing in like 99.9999% of it, kind of, right? Except for you have these tiny little clusters of matter that's held together. Planets, stars, asteroids, right? You clump all the mass tends to stick together. And atoms and molecules do that as well. Now, in the universe, it's mainly due to gravity, but you can kind of think of gravity as like an intermolecular force, holding all the different objects in space together. Now, our things today we're not worried about their gravity as much. We're worried about their charge, usually their electromagnetism, being the reason that they tend to stick together. So, the stronger the IMF, the more molecules, your atoms or molecules, are held together. So the higher your intermolecular forces, the stronger that force of attraction holding you together, and the harder it'll be to separate that group of atoms or molecules. Stronger IMF means a stronger bond. And I put that in quotation marks very intentionally because intermolecular forces are not bonds. Not at all. They're not as strong as a covalent or an ionic bond, which are intramolecular forces. And things with higher intermolecular forces have a higher boiling and melting point. So if you're comparing two different like a bottle of an alcohol versus a bottle of water, you can compare the two and like which one of them will have a higher melting or boiling point, right? So like alcohol evaporates before water does if you're heating them at the same time. Water evaporates at a higher temperature. It has a higher melting or boiling point. The reason why is because water has really high intermolecular forces and alcohol has slightly lower. So a lot of their boiling and melting points and other things too, like vapor pressure and all these things we're going to learn about, have to do with their intermolecular forces. but they are not considered bonds. They're weaker than a normal traditional bond. Okay, so I have a drawing here, and this drawing is scattered full of both inter and intramolecular forces. So if you take a look at it, okay, any solid line, like here I have a water molecule. These solid lines are covalent bonds. Those are intramolecular forces. These are the forces holding this water molecule to itself. And then I have this dashed line. The dashed line here is this hydrogen on this molecule being attracted to the oxygen on this molecule. And we represent that with a dashed line. So these things aren't physically bonded to each other. They're just attracted to each other. And we'll kind of learn the reason why is because we've talked about polarity before. The hydrogen has a slightly positive charge and the oxygen has a slightly negative charge in the water molecule, which is what causes them to be attracted to each other. Okay, but this attraction is just that, just like kind of imagine like a magnet and they're kind of attracted to each other. This bond, you would need a chemical reaction to break it. To break this attraction, I would just have to like apply a little bit of a force and separate the molecules. And you can see this picture, you have any of the regular solid bonds or intramolecular forces, they're way stronger. And then any of the dashed lines are intermolecular forces, just attraction between molecules together. Okay. The first kind of intermolecular force we're going to learn about is called the London dispersion force. You'll see it abbreviated a lot, capital LDF, London dispersion forces. Now, they are important. They are the weakest type of intermolecular force. Usually, okay, we'll talk about the comparisons later, but usually they're considered kind of the weakest type. But every single atom or molecule has London dispersion forces. In fact, anything at all that has electrons, even one electron, has a London dispersion force of some amount. They are the main reason that neutrally charged things and other nonpolar things are attracted to each other at all. If we're just looking at drawings of like two non-charged, non-polar molecules, there should be no reason for them to stick together, but they still tend to. And London dispersion forces helps to explain that. Now, to think about it, we need to think about the electrons. The electrons are what really come into play for London dispersion forces. So this one's a little bit more advanced than the other ones, I think. So this is a word description, and then we'll kind of do a picture drawing the same thing. But just to start with our word description here, electrons move independently of each other and can appear at any place in an electron's cloud. So if you have your nucleus in the middle and your electrons somewhere in that orbital, or in their orbitals, right, they could be kind of in random positions in the electron cloud. And we can take a snapshot of the atom and see where those electrons are at one moment in time. By random chance, at that one moment in time, there might be more electrons on the left or more electrons on the top of the atom, or just randomly somewhere in the atoms you might have more electrons. And for that moment, that side of the atom will have a partial negative charge, which means the other side must have a partial positive charge. Okay, so to kind of talk about that, so we have a nucleus in the middle, that doesn't really change, and we have an electron cloud. Now my electrons can appear pretty much anywhere in here independently of each other. So let's just say I froze time and the electrons in my atom are like here. Okay, they should be more spread out, but just due to random chance, I have 6 of them on this side and only 1 on this side. So this atom at this moment would have a partially negative charge on this side of the atom, kind of. And this side that's lacking electrons a little bit would have a partial positive charge, right? And that's just because this side has more negative charges than it expects. This side has less negative charges than it expects. Okay. Well, this is kind of something that can happen by random chance. And when it does, this is called a temporary dipole. This word dipole is going to be very important to this lesson. Dipole just means you have a positive and negative end. Now, this only happens temporarily due to these electrons. We've kind of frozen time, right? So only at this instant where you have more electrons on this side do these charges exist. If I just let them whirl around for a couple more seconds, I can even draw another atom over here. If I just let the electrons whirl around independently, maybe they would be more on this side, or maybe they'd be more evenly spread out, or maybe there'd be more all at the top or something. So this is just a temporary effect. But what happens when you have a temporary dipole like this? these charges are going to lead to attraction. And let's kind of talk about how. Since this is a negative charge here, the electrons in this atom are going to be temporarily affected by this negative charge. Electrons are repelled by negative charges. So any of the electrons that were on the left, it's going to be a little bit more likely that they're going to show up on the right, because they're being repelled away from this negative charge. And now that actually induces, is the fancy way to say it, a dipole on this atom, where this side over here is a negative charge, because look at all these negatively charged things, and this side is now positively charged, because all the electrons are gone. Okay, so if one atom gets a temporary dipole, or a group of atoms does, it kind of affects the atoms around them. And it's just creating, for small moments in time, all these positive and negative sort of charges. And all this leads to is that any positive or negative charges attract each other. And that's the London dispersion force. Okay. When something has an induced dipole or a temporary dipole due to its electrons being randomly distributed more on one side than the other, that kind of induces a dipole on atoms around it as well, and it leads to them kind of being attracted to each other a little bit. Okay. This force is really relatively weak unless you have just like a massive amount of electrons here, because it is just temporary. So this might happen for one moment in time, but then these electrons move about their day, and then if they go back maybe to like a more even arrangement, then these charges are gone. And then there wouldn't really be London dispersion forces until another atom happened to by random chance be split differently. So it's kind of like not always occurring. But if you're imagining you're having trillions of atoms on top of each other, it's always occurring in some of the atoms. And it just leads to this sort of chain reaction effect of a net attraction towards each other. Okay, so kind of the main idea here. Every force we're going to look at today is a force between a positive and negative charge. But a London dispersion force is just a temporary positive or negative charge caused by the random position of electrons in the electrons' clouds. So that's kind of a lot. Here's kind of a picture showing the same thing drawn a little bit better. If I put this atom that we're just talking about, this randomly, this one's very dramatic, right? We have all these electrons over here. If I take this and stick it next to another atom, right, it's going to, this positive charge would attract these electrons and induce a dipole in this atom. And then the electrostatic attraction between the positive and negative charge would be the reason that they stick together. The atoms on the electrons in the second atom are going to be attracted to the positive end of the first atom. And you can imagine this kind of creating a chain reaction throughout the entire sort of sample, leading to a little bit of attraction between all the molecules. Okay. In London dispersion forces, each atom is still overall neutral, right? There's no actual charges in the atom, but the atom has a dipole moment. A dipole, as we said, means you have a negative end and a positive end. And the dipole moment is just in that moment in time, right? What is your situation with positive and negative charges? Where are they located? The two dipoles attract each other. So to summarize here, neutral atoms attract each other because the random positions of electrons in electron clouds produces temporary dipoles that lead to attraction between atoms. The force is pretty weak, but occurs in every single atom or molecule because they all have electrons for this effect to occur. So this is kind of our baseline starter intermolecular force that everything will have. Okay, now to compare the London dispersion forces of different atoms, we've kind of given it away this idea that the more electrons you have, or the larger your electron cloud is, the greater your London dispersion forces are going to be. So atoms with more electrons have more London dispersion forces and therefore more intermolecular forces. There's a really fancy scientific way to say this. So things that with more electrons or with a bigger electron cloud, you would say that they have a more polarizable electron cloud. If we break down that word, polarizable, ability to become polar, ability to have those positive and negative charges. The larger the electron cloud is and the more electrons that are in it, the more possibilities you have for these imbalances of electrons, where one more end up on one side than the other. And the more electrons you have, the greater the magnitude of these electron imbalances can be. And the way we say that is it has a more polarizable, more able to be polar electron cloud. Okay. So which of the following noble gases would you expect to experience more London dispersion forces? Helium or xenon? Okay. So a little bit, we have helium, xenon. We just want to compare their London dispersion forces. So no other types of forces we care about here. So what I'm going to do is I would find each of them on my periodic table. The easiest way, the most common way you'll see to compare London dispersion forces, all you have to do is look at molar mass. The greater molar mass equals the greater London dispersion forces. So the more molar mass you have, the more your London dispersion forces. Now, it's not the actual weight. That's kind of important. This is how we test to see which one has more. It's not the weight of the atom, the protons and neutrons that are actually affecting this, but it's just kind of our general trend here. The bigger something is, the more its molar mass is. So you just use molar mass as kind of your guide to help you, but it's not actually the mass of the atom causing it. It's just the size of the electron clouds. But it just kind of works that the bigger something is, the more electrons it has, and the bigger its electron cloud tends to be. So all we're going to do is compare how heavy these things are. And helium's really small. It has an atomic mass of 4. And xenon is quite big. I don't know exactly how big xenon is, but it's like way bigger than helium. So I should be professional and look it up. Okay. And we got it here. We got xenon weighs 131.294. Okay. So because of that, that's all the information I need to know that xenon has more LDFs. We could write that in words, and we're going to practice this a lot because this is constantly a question. So like the most formal way you could answer this sort of question is you could say xenon has a larger, more polarizable electron cloud, and therefore it has more London dispersion forces. Therefore, it has more total intermolecular forces as well. So something like that could be your full best answer for explaining the difference between those two London dispersion forces. This question is not asking about total intermolecular forces, just London dispersion forces, so you want to need that last little part there. Now, the second question is related, should xenon or helium have a higher boiling point? And I have the answers down here just to kind of talk about it. But all we need to do is go back here. Xenon has more LDFs. Therefore, it has more intermolecular forces total. Therefore, it has a higher boiling or melting point. I forget which one I asked, but they go the same way. So because xenon has more London dispersion forces, it therefore has more intermolecular forces, which means it therefore has a higher melting and boiling point. The greater your intermolecular forces holding all your molecules together, right? If you have a bunch of xenons, the more attracted they are to each other, the greater this attraction is, the more energy you need to separate them, which means you're going to need higher temperatures or higher energy to be able to split these things apart and to melt them or to boil them. And this last part's a little confusing. We're going to talk about this in more detail, but I just want you to see it a lot because this is the most common sort of question asked about intermolecular forces, is how it relates to melting and boiling points. And here we have the data. We have their boiling points. We have xenon is -1, what's my brain doing? -117 degrees Celsius, 117, there it is. And helium is -272. So they're both really low boiling points, but xenon's is much higher, right? It's 160 so degrees higher than helium's because it has way more intermolecular forces. Okay. London dispersion forces are generally weak, but very large molecules, especially those with large surface areas, can experience a lot of attraction overall from London dispersion forces. The larger a molecule gets, the more important London dispersion forces become. So for tiny little molecules, they're going to be kind of pitiful. They're not that important. But when you get to really large like macromolecules, or you're talking about even really heavy elements, things like iodine or something, right? That's like pretty far down on the periodic table. They have a lot of London dispersion forces. For very large things, London dispersion forces can even be stronger than things like hydrogen bonds, which we'll talk about as typically the strongest type of intermolecular force. So we have one more sort of weird example, one other situation you can get with London dispersion forces. Here I have some different molecules, and if you count all the atoms, right, I have 4 carbons and I have 10 hydrogens. I have 4 carbons and I have 10 hydrogens. N-butane and isobutane are essentially the same. You'll learn more about these in like organic chemistry, but these are like structural isomers. They are exactly the same, but they're just rearranged in a different shape. Because they have the exact same atoms, they would have the exact same mass. So to think about which one has more London dispersion forces, our normal trick doesn't work. We can't just pick the one with the bigger mass because they have the same mass. The second way you can sort of compare London dispersion forces is thinking about how effective they're being, right? We need to think about the surface area of interreactability. I just made that up, right? But the idea is, how close are these molecules able to get to each other? Because the closer you're able to get to a dipole, a positive and negative charge, the more attracted they'll be. So if you look at something like isobutane, right, this weird shape makes it really clunky. This molecule can only get its hydrogens or its carbons near like 1 or 2 other hydrogens. You can't really layer these things effectively so that you have like the maximum surface area touching. And that's actually going to get in the way of their attraction a little bit. These experience London dispersion forces, but in N-butane, they're actually much greater. These flat molecules can get a lot closer to each other, and since they can get closer to each other, they still have the same mass, so they have the same polarizability, but they're able to reduce the radius between the dipole. And that will also lead to an increase in intermolecular forces, in London dispersion forces specifically, which means N-butane has a higher boiling point. It takes more temperature to boil a sample of N-butane. Because the molecules can get closer, they experience more relative London dispersion forces. Now that's kind of weird, and it's kind of more advanced than we typically need because we don't think about molecule shape for hardly anything. But this one example I see a couple of times, so just kind of keep this in mind as well for comparing London dispersion forces. If you see molecules based on their shape, kind of the more flat ones have more intermolecular forces because they can get closer to each other. Now, the one example I know this for is for like in biology, you would use this. You might have learned about like saturated versus unsaturated fatty acids. So I'm just kind of sketching it real quick. There should be 3 tails, but whatever. Sure, Strawman. This is a saturated fatty acid. Saturated means that you are completely saturated with hydrogen, meaning that this is like a carbon chain, right? And you'll see carbon chains drawn like this. You don't actually have to draw the carbons, but each of these sort of vertexes here would be a carbon atom. And those carbons actually have some hydrogens attached to them and stuff, but for reasons, we don't have to draw them for a molecule like this. Now this one's saturated, which means its tails are supposed to be perfectly straight. Now my drawing's not perfect, but you'll have another type of fatty acid called an unsaturated fatty acid. Okay, which has some tails that are straight, but then there's a double bond that messes up the shape. And it becomes all like crooked. And it can get even more severe than what I drew it here. So I could have like a double bond here that messes up the shape. Maybe another double bond that messes up the shape, and so on. This is called an unsaturated, right, triglyceride or unsaturated fatty acid. So these, because all of these tails are straight, the distance between them is a lot shorter. And they actually have a higher melting point and boiling point because of that. Because these tails are able to get closer to each other, they experience more London dispersion forces, right? And that means they have a higher intermolecular force and higher melting and boiling points. Saturated fats are things like butter. They are solid at room temperature. Because it takes more energy to melt them, they are solid at room temperature. Unsaturated fats with all these sort of crooks in it, right? Some of these atoms are close to each other, but then you get these weird distances, like this radius is really big. So you would experience less intermolecular forces between these two tails, right? Because of that, it has a lower melting point and boiling point. Unsaturated fats are things like oils, which are liquid at room temperature. Okay, they've already melted, is a way to think about it. Because of their lower melting point, they melted at a lower temperature and are liquid at room temperature. And you might have learned about these a little bit, but this is actually the reason why these things are the way they are. Why solid or saturated things are solid is actually due to London dispersion forces between the tails. And unsaturated forces are liquids because they have less London dispersion forces because their tails are weirdly shaped. They don't lay as flat on top of each other and aren't as attracted to each other. Now, you might have heard about these with like nutrition angle too. Unsaturated fats are generally considered healthier for you than saturated fats. Neither of them are considered healthy, right? They're still fats. But maybe I should phrase it the other way, where saturated fats are more dangerous. These can lead to, or more likely to lead to, like heart disease. So you might have heard of like diets where you're supposed to reduce the amount of butter and stuff you eat and replace it with like olive oil or something. And that's better for your heart because saturated fats are solid at room temperature, which means in your body, they form solids. So they can lead to like clogs in your artery and stuff like that over time because you have solid pieces of the saturated fats left behind. Liquids can travel through your arteries and through your cardiovascular system a lot easier because they are liquids. This isn't part of our class, but there's a good example of London dispersion forces and dietary advice from Mr. Winstead. Yeah. Next is dipole-dipole forces. So this is our second type. London dispersion forces definitely have the most going on. Dipole-dipole is a little bit simpler. They're just forces of attraction due to molecules being polar. Polar things attract other polar things, and each polar molecule has a dipole. So when you have two of them next to each other, they're called dipole-dipole forces. A dipole, again, is just something with a positive and negative end. A dipole-dipole force is the attraction between two dipoles. This is now generally stronger than London dispersion forces because these dipoles are permanent. You have a permanent positive and negative end. Right? They're not just happening due to random positions of electrons sometimes. And that's what makes them stronger, is that these are permanent forces that are always at play. Okay. Dipoles will orient themselves so that the negative dipoles of one molecule are attracted to the positive dipoles of another one. This extra attraction makes the molecules more difficult to separate, and by that we mean melt or boil. Right, I have my negatively charged chlorine because it's more electronegative than the carbon. So I would know that this polar molecule has a negative side here. The negative chlorine here is slightly attracted to the positive carbon on the adjacent molecule, and so on. And every single CH3Cl molecule here would be attracted to each other because of their dipoles. And this is just the dipole-dipole force. Again, we're drawing it with a dashed line because you need multiple molecules together to be attracted to each other for an intermolecular force. And all you need to know is all polar molecules experience dipole-dipole forces. Non-polar molecules will not. So H2O experiences dipole-dipole forces because it's polar. So that's all you need to know. It's important to remember, though, that this means multiple H2O molecules are attracted to each other, not a single molecule. A single molecule by itself does not have intermolecular forces. A single molecule has a positive and negative end, but it's not attracted to anything because there's nothing else to be attracted to. You need groups of molecules to experience these forces. Okay, so here I have some water molecules drawn. Oops, all right. And water molecules would have the O side being partially negative and the H sides being partially positive. And so they're going to arrange themselves, particularly in these patterns, to maximize that attractive force. Right? The positive charges want to be near the oxygens, and the oxygens want to be near the positives. And they're kind of orienting themselves in space, so that could be true for everything. Now, the main issue I see with this drawing is actually these are close to each other. That's not okay. This should have been rotated around like 90 degrees down so that this oxygen is facing the hydrogen closer. But maybe the picture, we ran out of room or something. Water molecules in solutions will also be attracted to ions. And this is a little bit more chapter 8, where we're going to talk about next time. But this chlorine ion has a negative charge, so you can kind of see all these water molecules, the positive ends are facing it, the hydrogens are facing it, right? Because they're attracted to each other like little magnets. But if you have a positive ion, you see all these oxygens flip around so that the negative thing is attracted to it. Polar molecules like water are really good at dissolving things with like ionic bonds, things with positive and negative charges, because they really like to be interacting with each other in this sort of pattern. This is called actually the ion dipole force. This is an ion, this is a dipole. So if you ever see that phrase, we're not really going to bring it up separately, but an ion attracted to a dipole is this interaction or this interaction. And the last type, that was it for dipole-dipole forces, really. You just figure out if it's polar or not. And hydrogen bonding is the last type. It is kind of substantially the strongest type. Unless you have a really, really giant molecule, hydrogen bonding is always the strongest. It's another type of dipole-dipole force, but it's an especially strong and special type. And there's only 3 possible examples of hydrogen bonding. And they all involve a hydrogen atom, which is where the name comes from. And that hydrogen is bonded to one of 3 of the most electronegative atoms: nitrogen, oxygen, or fluorine. These 3 elements are the most electronegative ones we have, which is why only they make this special bond with hydrogen. Things with hydrogen bonds have abnormally high melting points and boiling points. So they don't follow the trend of normal dipoles, where the more polar a bond is, the greater its melting point and boiling point. But they follow that, I guess, but they follow it. There's like a big jump with these 3 bonds specifically. These 3 bonds give it like extra polarity. And the reason why is like some really complicated reasonings why. But what I like to say is hydrogen is the smallest atom. It's kind of weak, easy to bully. It really wants to get rid of that 1 electron. And these are the 3 biggest bullies that we have. Nitrogen, oxygen, and fluorine are the most electronegative elements. So they're trying to take electrons the most. So when they bond with hydrogen specifically, hydrogen's kind of weak and pathetic, easy to bully. These things are really strong. They want to bully something. So it just kind of works out very specifically with these 3 to make an extreme polar bond. When you have a molecule with one of these 3 bonds, HO, HN, or HF bonds, your sample has hydrogen bonding. We said water before has hydrogen bonds, right? And this is them being shown. Now again, this isn't a single molecule's bonds. We're not caring about the fact that this O and H are bonded. It matters, but the reason it matters is because this O and H bond creates these charges. This charge with this hydrogen bond here would be exceptionally strong. This positive is just a little bit stronger than the positives on a regular dipole-dipole bond. And this negative is a little bit stronger than the normal negatives on a dipole-dipole force. And just because of that, this same interaction, the same force, is just stronger than you would expect because of the atoms bonded. And the graph here is kind of complicated, but it kind of shows this idea. So you have a trend with similar compounds here. So you have hydrogen bonded to tellurium, selenium, sulfur, and oxygen. Well, why those 4 things specifically? Let's take a look at periodic table. And those 4 elements were these 4: oxygen, sulfur, selenium, tellurium. Everything in the same row, which means they generally have similar properties. Okay, and what we can kind of see on our graph here, that's not our graph, this is our graph. Those 4, the boiling point sort of goes down over, like this is the biggest one. Then this one, it's a little bit lower boiling point. And this one's a little bit lower boiling point. But it doesn't follow the trend all the way down. Now this trend makes sense because each of these, let me pull this back up. Each of these in this trend should be going down because the atom's getting smaller. So this is going down a little bit because the London dispersion forces are decreasing. And we would expect, if everything was the same, H2O maybe should be something like this. But you see it's not. Instead, it's way up here. So it jumped significantly in boiling point with H2O because you have an O and an H bonded together. And all these other things display a similar trend. What you would expect is this green line here, right? I have tin, germanium, silicon, and carbon. So that's all the elements in the same row as carbon. And you just notice that their boiling point goes down the smaller they get because their London dispersion forces are decreasing, right? Or you can think about it backwards. As the molecules get larger, their London dispersion forces increase, and therefore their boiling point increases. But these are the only three atoms that are bonds, I guess, that break the trends. When H is bonded to an O, an F, or an N, it just makes an especially high boiling point or melting point bond there because of the hydrogen bonding. So these three have it because they have hydrogen bonding, but carbon bonded to hydrogen is not a hydrogen bond. So that's why this one follows the trend, unlike the other three. Okay, so that graph just kind of there to display it. It might be a little bit confusing to sort of look at it. Maybe you can come back to it later once we've learned a little bit more about it and done some practice. Maybe I'll give you a quiz question with this sort of graph and try to help you explain it. But we need to practice it a little bit more first. So the most common types of questions are ones like these. So what type of IMFs are found in these molecules? We have CH4, we have pH3, we have CO2, we have HF. All right, my document camera is frozen. One moment.